Hey there. Okay, so this lesson today, we get introduced to a new way to integrate. We have a new integration technique, and the thing about integration, as opposed to derivatives, is first of all, some things just can't be integrated by hand, and so we learn methods to deal with that. But the way a problem is set up kind of determines how you have to attack it. And in A/B calculus, really all you learn are, your basic power rules, U substitution. That's kind of it. You have some inverse trig in there, but I want to show you these three things here and to show you where we are headed and why we have to do what we're about to do in this lesson. So I have three different integrals here that all look kind of similar. They all have quadratics on bottom, but the numerators all look a little bit different as well. And we have to be pretty good at recognizing what strategy we have to employ to integrate. There are some colleges I know that have like integration bees, like contests just for integration. I know Wabash has an integration bee. I think MIT has an integration bee where they have contests like who can integrate the best. I know that sounds weird. So this very first one, if I'm looking at it and thinking about what we've learned already, if I notice that if I had u be the denominator, you don't need to write this, I just want you to watch. If I had u be the denominator, and I took the derivative of both sides, now I notice that I can replace 1 plus x squared with u, and I can also replace x dx with du once I divide both sides by 2 and go through u substitution. My point is u substitution works in this case. If I look at the second one, well, I can't use u substitution because if I have u be the denominator, well, then the derivative is 2x, and I don't see an x show up anywhere. I get stuck, is what I'm saying. And the way we have to attack this one, well, this one is arctangent. This is just one we have to be able to recognize. Out of all of the inverse trig integration rules, this is the one that I would most definitely know. I can't promise any will show up, especially not many, but this is one I would for sure know. And then I look at the last one. This is where this is the lead-in, if you will. So the last one, okay, look at what happens if I have u be the denominator. Let's say, okay, we're going to go ahead and we're going to integrate this, la-di-da. Let's use u substitution because that's all we know how to do right now. And then I get here. And now I notice that I'm trying to replace x minus 19, and there's really nothing I can do with 2x minus 3 to make it become x minus 19. My point is, we're stuck. All we know is u substitution. It doesn't work. Inverse trig, this is not set up for that. So there's nothing we can really do at this point in time. So enter partial fraction decomposition. So I'm not going to read through all this, but here's what I want to kind of explain of what's happening. I want you to look at this very top line of equations, and I'm actually going to have you focus on from right to left. This was the fraction right here. This was the fraction we just tried to integrate, and we couldn't integrate it. But here's the deal. There were two other fractions that were being added or subtracted to get to this fraction. In fact, this right here, this fraction can be broken down into these two fractions being subtracted. And it's basically their equivalent. And I would actually be able to integrate these two fractions separately right here. I would be able to integrate those with natural logs that we're going to be getting into. So if only we had a way to figure out, okay, if I have this fraction to start with, how can I figure out what the fractions were that were being added or subtracted so that then I can integrate those smaller fractions easier? And in finding the breakdown, that's why it's called decomposition. We're decomposing the original fraction into its parts. That's the idea today, okay? Because once we break it down into multiple fractions, we're then going to be able to integrate those multiple fractions a whole lot easier. In fact, if you look at this next line right here, to integrate those two fractions, if you remember, this is just where natural log comes into play. The integral of 1 over x plus 2 is natural log of absolute value of x plus 2. So that's what we're going to be getting into, okay? So let's get into how do we figure out what the fractions were that were being added or subtracted. That's the whole idea. And I guess, the big idea is how do you know when you're going to have to do this? How do you know when you're going to have to do U substitution, when inverse trig, when partial fraction decomposition? And it all starts with the denominator. Here's your tip-off. If the denominator can be factored, then you're going to be doing some form of partial fraction decomposition almost always. I can't think of a time that you won't. So the first thing we need to do, if I look at this first one and I want to integrate 1 over x squared plus x minus 2, well, we know U substitution won't work because if U is the bottom, the derivative of that doesn't show up in the top. It's not set up for arctangent or inverse trig, but it does factor. Those are kind of my thought processes that I go along to my integration techniques. It does factor. So I know it factors into x plus 2, x minus 1. Now here's our process. Here's our strategy, okay? This is our setup. So I'm going to rewrite that fraction. Forget about the integral sign right now. I'm going to rewrite this fraction. 1 over x plus 2, x minus 1, equals, and I'm going to set up this way. So what I'm going to do is put a, I'm trying to figure out what that constant a is, over the first factor, plus b over the second factor. And the whole goal, I'm trying to figure out what a and b are. So I break it down into the two factors, but I'm trying to figure out what those constants are on top. So here's the next thing we do. In Algebra 2, when I teach Algebra 2 and we have equations with fractions in them, I try so hard to get students to clear the fractions in order to solve it. We look for a common denominator and we clear the fractions. And in fact, you're not going to have to do this step every time, but I'm going to show it here just to give a visual. If I multiply everything in this equation by x plus 2, x minus 1, all the fractions will go away. Again, you will not have to do this step. You can kind of do it in your head, you'll see. So if I multiply everything by x plus 2, x minus 1, x plus 2, x minus 1, and then even over here on the left side, x plus 2, x minus 1. And now I clear out whatever I can. So on the first fraction, both factors cancel out. And all I have is a 1. On the right side, the x plus 2's cancel. And so all I have left is a times x minus 1. And then the second fraction, the x minus 1's cancel. And I have b times x plus 2. So I'm going to wait a second for you guys to see what just happened here. And you can see why you're not going to have to show that step every time. Basically, what's going to be left are the factors that aren't in the denominators. Like for that a fraction, x minus 1 wasn't in the denominator, so you have an x minus 1 left next to it. And same with the b. Okay. Here's the next step. In math, you get to pick any numbers that you want to plug in for x. That's like your independent variable. And so what we're going to do now, imagine that I want to get this factor right here, this thing right here to go away. Think about what you would plug in for x to make that whole thing disappear. And that would be 1. So I'm going to pick numbers to plug in for x that are going to make those factors become 0. So let's look what happens if I plug in 1 for x. Okay, if x is 1, let's see what happens in this whole equation. Well, I would still have 1 on the left side. The highlighted thing goes away. And then, again, plugging 1 in for x right here, I would have 3b left over. So I have 1 equals 3b, which means b is 1/3. And that's what we were after to begin with. We were trying to figure out what those a and b values are. That's the whole goal in this process. Okay, so now I go back to, I like to say I go back to the drawing board. So I go back to that line right here. And now let's try to figure out what a is. So now I'm trying to cancel out, I'm not good at transitioning my colors like Sal Khan, but now I'm trying to cancel out this thing right here, the b. So now I'm going to plug in -2 for x. What happens if x is -2? Well, I'm still going to have a 1 on the left side. And then I'm going to have -3 from the -2 minus 1, -3a. And the pink stuff's gone. So a is negative 1/3. Okay. So what that means is this. I know what the a and b values are. I'm running out of room here. Maybe I could zoom out. Oh, I still have, look at all that space I got over here. Okay, I was worried. All right, so here's what I know. I now know what a and b are. So that original fraction, instead of having the original fraction in there, now I can split it up into, well, what was it? It was a over x plus 2. So negative 1/3 over x plus 2. Plus, and then b was 1/3. Oh, crap, I didn't write that very well. Over x minus 1. And if you want to think about this, I know this looks really, really gross. And so a different way that you could think about this, instead of looking like this, maybe this will help, is pull those constants out in front of the integrals. Like, I basically have negative 1/3 times the integral of 1 over x plus 2 plus, and then let's say I pull 1/3 out in front of the second fraction. And now I'm just integrating each of these. So the first one would become negative 1/3 natural log of the absolute value of x plus 2. Oops. Plus 1/3 natural log of absolute value of x minus 1 plus c. Out of all, this is going to sound really weird, but out of all the integration techniques, this one is actually my favorite. I don't know why it's so satisfying to me that you're breaking down a fraction into smaller fractions so that you can integrate. I just think it's cool. How it works that way. But this only works if the denominator can be factored to begin with. You know, if I gave you this same problem and the bottom couldn't be factored, quite frankly, I don't know how we would go about integrating it, or even if you could. All right. Let's look at the next one. You could try it if you want, but so first thing I notice is the bottom can be factored. So I'm going to do that. The bottom is going to become, I can take an x out, and then I would have x squared plus 2x minus 3. So then that would become x plus 3, x minus 1. So hopefully we're pretty good with our factoring. So then what I do, I take that original fraction in factored form. Now here's the deal. However many factors in the denominator that you have with x's in them, that's how many fractions you're going to be creating on the right side of the equal sign. And so I'm going to just put each factor in the denominator over here. So it'd be a over x is the first one, plus b over x plus 3, plus c over x minus 1. And again, the goal is just figuring out what a, b, and c are. Okay, so this is the point now where I want to clear all these fractions. I want to multiply everything in this equation by x, x plus 3, x minus 1. Basically, I want to multiply everything by this denominator right here. And we don't have to write that out. That'd be a lot to write out, and it gets messy. So we can kind of do some of this in our head. So on the left side, it's still just 2x squared minus 9. That bottom cancels out. On the right side, the x would go away, but we would still have x plus 3, x minus 1. The middle fraction, the x plus 3, would go away, so we would have an x and an x minus 1. And then for the last one, the x minus 1s cancel, so we would have c, x, x plus 3. Once we've cleared our fractions, now is the point where we pick numbers to plug in for the x's to get some of these things to go away. This is kind of, in my opinion, the fun part. I don't know if it's fun or not, but you guys are weird, so I don't know. You guys might think it's fun too. So you could do this in any way, but I notice if x is 0 right here, if x is 0, then both of these things are going to go away. So I'm going to have x be 0. Let's see what happens if x is 0. Well, on the left side, I would have negative 9. From the a part, I would have, let's see, 3 times negative 1, so negative 3a. And then the pink things are going to go away. So a is 3. All right, let's pick the other x values. Well, let's have x be 1, because that'll make the a and the b's go away. So let's have x equal 1. So let's see, that would be 2 minus 9, negative 7. The a and the b things are going to go away. Plug 1s in for the other x's. So we would have 4c. So c is negative 7/4. And then we want to plug in negative 3. Let's see, 18 minus 9 is 9. The a will go away, the c will go away. So we're going to have, let's see, negative 4 times negative 3 is 12b. So b is 9/12, 3/4. And so now if I was going to split up this fraction, what this would look like, well, a is 3, so we would have 3 over x. B is 3/4. Make sure you put the right numbers over the right denominators. So x plus 3. And then c is negative 7/4 over x minus 1. And anytime you're integrating and you just have a x, like a linear thing on bottom, it's always natural logs. That first one would be 3 natural log absolute value of x. The next one would be 3/4 natural log absolute value of x plus 3. And then it would be minus 7/4 natural log absolute value of x minus 1 plus c. So the answers look pretty gross, but at least having this process or having this method allows us to actually integrate. Isn't it swell? Okay. Last two. I would encourage you guys to go ahead and try these two. The last one, so here's the deal. The first two, I should put an example in there when it's not just, x or x plus 1 or x plus 3, but if it turned out to be like 2x plus 1, then what would happen? So just a real quick refresher that if you were integrating like 1 over 2x plus 1, that it would not be natural log of absolute value of 2x plus 1. You technically would have to go through u substitution. I tried in first semester to give you guys that little shortcut where if you have, some constant in front of that x term, you're going to have the reciprocal of that on the outside, so that you would have a 1/2 on the outside. I tried getting into that when we were integrating e to the 2x. I said, yeah, you can go through u substitution, but with such a basic one, it's going to be e to the 2x, and you're going to have a 1/2 out in front. So that does turn out to be a nice little shortcut for us. Anyway, I would pause it if I were you guys and try these last two. And I'll work them out after you try them out. All right, I was just going to write the answer, but I don't know. Maybe I'll write the answer, and then if you have questions, you guys can let me know. So here's what the answer should be. Negative 2/5 natural log absolute value of x plus 3/7 natural log absolute value of x minus 2. Oops, dang it, did that again. They really don't take off on a free response for parentheses because they don't want a grade handwriting, but I would just make sure that you try to write neatly. Minus 1/35 natural log absolute value of x plus 5 plus c. Don't forget plus c. If you didn't get that or had some issues, email me and I'll work through that with you. But that way I'm not taking up some of your time. If you guys did get that correct, you don't need to see me work it out. The next one is a definite integral. So I do want to make sure I go over this one, and then we'll be done. So I first notice, okay, U substitution doesn't work. It's not inverse trig. Hopefully that can be factored, and it can. We need to have a factoring technique when there's a number in front of x squared, you know, whether that's guess and check or the AC method in Algebra 2. Some people do slip, slide, divide. Whatever method you have, we have to be able to factor that. But it turns out to be 10x plus 1 and x plus 1. So I'm going to have a over, I had this different on my notes, so I'm going to do it the way I had it. I'm going to write the 10x plus 1 first. Right there. Clear the fractions, so 9 equals a times x plus 1. And then b times 10x plus 1. I'm going to plug in negative 1 for x. So then I get 9 equals negative 9b. b is negative 1. And then I'm going to plug in negative 1/10. Because that, I'm trying to figure out what makes these little factors become 0. And so that'd be negative 1/10 would make that 0. So I would have 9 equals 9/10 a. Multiply by the reciprocal there, and you get a is 10. Okay. So now I'm technically integrating from 0 to 8 of 10 over 10x plus 1 minus 1 over x plus 1. And now with a definite integral, remember, we have to integrate first. So this first one is kind of interesting because you have that 10 on top. But notice we have that 10x on bottom here. So like technically it would become 10. I'm going to write this out so I don't confuse you guys. It would be a 10 from the numerator. And then natural log of absolute value of 10x plus 1. But then we would also have a 1/10 out in front to combat that 10. That's what I was trying to talk about. So we would have a 1/10 out in front. So the 10 and the 1/10 will cancel. So we just get natural log of 10x plus 1. And then minus natural log absolute value of x plus 1. From 0 to 8. And now we plug in 8. So I would have natural log of 81 minus natural log of 9. That's from plugging the 8s in. And then minus parentheses, I would have natural log of 1 minus natural log of 1. Now we just have to remember some log rules, some log properties, so be careful here. First of all, natural log of 1, any log base of 1 is just 0. So that whole part right there is just gone. And then we have natural log of 81 minus natural log of 9. I don't know what either one of those are individually. And I also noticed in the answer choices, that's not the answer. But going back to Algebra 2 and pre-cal, remember when you're subtracting two logs, that's the same as one log, but dividing the arguments, dividing the things inside. Not subtracting them, but dividing them. So that would be natural log of 9. So C. So that's partial fraction decomposition. Kind of a cool method, in my opinion. I like it. It can get a little more advanced. I don't know when you guys go off to school if it gets even harder. In terms of what's assessed on the AP test, this is what you'll be doing. But technically, you can get into some problems where, you know, what would happen? You don't need to worry about this, but what if one of your factors was like squared? What if it was like x plus 1 squared here? Now some issues arise. You can still do it. It's just tougher, but you're not going to have to worry about that from what I've been told. So kind of nice. All right, let me know if you have any questions.